Bismillahirrahmanirrahim. Assalamu alaikum to the week 3 lecture 2 of digital logic design. Course code is EEE241. We are discussing second chapter, that is Boolean algebra and logic gates. This reference and material is from digital design with introduction to Verilog HDL by Morris Menu, 5th edition. In our previous lecture, we discussed basic definitions, then definitions of Boolean algebra, and then we saw two-valued Boolean algebra. From this, we'll discuss this topic, two-valued Boolean algebra, and in this today's lecture, we'll discuss some basic basic theorems and properties. Basic theorems and properties which we can use in Boolean algebra, and these are postulates and theorems. Before going to postulates and theorems, see that we have a duality here. Duality means that binary operators are interchanged, and or. The identity elements are interchanged, that is 1 and 0. That and or can have both of them can have an identity operation, and for and we use 1, and for or we use 0. What I'm saying is that this first column, if you see here, that most of you will see plus sign, that is and operator, and or operator, and this second, which are with B's here, I have dot operator, that is or and operator. Plus is or and dot is and. So we have a duality here. Whatever operations or postulates or theorems we have for or, we have same for and. But for or, you will see mostly have 0 and 1s, and operator, 0 will be 1 and 1 will be 0. So starting with the postulate number 2, that says that if we have x plus 0, that if we have an x and we apply or operator on x and 0, we'll get x again. This we can simply prove by help of a table, or we can see later on that we can prove these theorems and with the help of postulates. So x plus 0 will be x, and if we apply an and operator on x and 1, it gives back x. So for or operator, 0 is an identity element, and for and operator, 1 is identity element. Postulate number 5 is that x plus x bar is equal to 1. All these postulates and theorems table is available in the book. So x plus x bar, that is the complement of x, will give 1. For an or operator, how that if we have an x, possible combinations are 0 and 1, x bar, that is its complement, will be 1 and 0, opposite of this. And if we apply an or operator on it, x plus x bar, for or operator, if any one of the elements or the inputs are 1, it will give a 1. But if we apply x dot x bar, that is and element, if any one of element is 1 but another is 0, it will give a 0. So here, so similarly, all these postulates can be proved by the help of making a truth table and applying the inputs and outputs on it, operations on it, and we can prove these. The theorem also says that x plus x is equal to x. That is that if we add or we apply an or operator on x and x, it will again give us an x. Say here, theorem number 1, we can prove that x plus x is equal to x. How? X plus x is equal to x plus dot 1. How I got this? From the postulate. Here you can see I'm talking about x plus x dot 1. You can see here, that when we have we can call the postulate number 2, b says that x dot 1 is equal to x. So here x plus x we assume in single element, for example we say it's y. So postulate 2b says that if we have y, it is equivalent to y dot 1. So that's why we have applied a dot 1 operator here. Applied postulate number 2b here. So x plus x dot 1. Now this dot 1 is here equivalent to x plus x bar is equal to 1. So we can apply postulate number 5a here. So x plus x and this 1 I have substituted with x plus x bar. How? By using this 5a postulate. Now again we'll come all these postulates we have seen. So now we'll apply. Now if we see postulate here 4b, postulates are used to solve for to prove the theorems. It says that x plus yz is equivalent to x plus y multiplied by x plus z. Same postulate I have applied here. X plus x bar means that x plus x bar, and then we know that x dot x bar is equivalent to 0. Where we have this x dot x bar is equal to 0, so we can apply postulate 5b with it on it. So this x dot x bar is 0, and then we are left with x plus 0. Again I'll go back. X plus 0 is equivalent to x, so we have x here. So for theorem 1a, which was x plus x is equivalent to x, we use these postulates to prove it. This is how we'll see how we can prove other theorems also using the postulates. So theorem 1, x plus x is equal to x. The same process we can use to prove x dot x is equal to x. Same postulate will not apply here. Duality concept will apply. It means, for example, if we applied here 2b, so probably we'll need 2a here. So theorem 1b is x dot x is equal to x. Its proof is written in the slide. We'll discuss later. Theorem 2 is x plus 1 is equal to x. X dot 0 is equal to 0. X bar and its bar means that if we take a complement of a number of x, an element, and then again take a complement, it will give us x again. Postulate number 3 is commutative. X plus y is equal to y plus x. Xy is equal to y of x. Theorem 4, that is associative. X plus y plus z is equal to x plus y plus z, and for and xy z is equal to xy and z. Distributive law we all know, postulate. Then comes De Morgan's. De Morgan's is widely used. It says that x plus y, that is if you apply an OR operator on x and y and then take its complement, it is equivalent to x complement and y complement. And here 5b, xy complement, that is we have AND operator in between it, between two values x and y. So xy ka AND le or then complement, it is equivalent to x bar plus y bar. Then we have absorption, widely used again. X plus xy is equivalent to x. X plus y is equivalent to x. So to prove all these postulates, we again and again have to refer to this table and of postulates and theorem. Theorem 1b, again, that as I mentioned, x dot x is equivalent to x can be proved, and it is a proof here given. Similarly as we applied the postulates. Now comes to x plus 1. Again theorem 2 can be proved that x plus 1 is equivalent to 1 dot x plus 1. As I said before, that if we have an element, if we add with 1, we'll get a x back. So here x plus, when we have considered a simple variable or a simple element and we have added with 1, again this one can be written as x plus x bar, as in the previous theorem we also proved. So x bar, then the distributive we get x and x plus x bar 1, x plus x bar 1. Now x bar and 1 will again give us x bar because of this postulate. X plus x bar is equal to 1. And same theorem 2b is that x dot 0 is equal to 0, and we can apply the duality operation here, which means that wherever we applied an OR we can apply a and wherever we have used 1 we can use 0, and where we have used 0 we have 1, and in this method we can prove the same this theorem using this same method. Theorem 3 is x bar whole. Again, complement of x complement is x, and our postulate number 5 already defines it. Postulate number 5 says x plus x bar is equal to 1, x dot x bar is equal to 0. So complement of x bar is x is also x bar whole bar. Now comes the theorem number 6, that is absorption. X plus xy is equivalent to, now we have wrote x as x dot 1 and x of y is same. So then this distributive x, we'll take x common as we normally say. We have x 1 plus y. 1 plus y is 1, so we have x dot 1 and x dot 1 is equivalent to x. And same this theorem 6b part can be proved by the help of duality. Again I repeat, duality means that the same process we'll apply, but where we have used AND gate or an operator we'll use or where we have used or we'll use and where we have used 1 we'll use 0, and where 0 and we'll have 1. And we can prove all these theorems, all these postulate by help of truth table, and which you should do as for your own to have a practice of these, how to solve the truth tables. Now comes the De Morgan's. As I said before, x plus y whole complement is equal to x bar plus y bar. This we can again prove with the help of truth table. Because we have two inputs, we'll have 4 combinations. Then first of all we'll apply our OR gate or OR operator on x and y. As we all know that if any one of them is input is 1, we'll get output will be 1. So we have this is both of them are 0, so output is 0, and rest of them will be 1 because any either one of elements is 1 or both of them is 1. Then we'll take its complement, that is x plus y's complement. 0 will become 1 and 1 will become 0. Now this is 1/2, that is the left side. Now we'll calculate the right hand side, and then we'll see both of them are equivalent or not. X bar, by taking complement of x, both of them the first two combinations were zeros, or we'll have 1, then 1s will become 0. Y bar, 0 will become 1, 1 will become 0. So in this way we have y bar, and then lastly we'll apply an AND operator between them. AND operator again says that if one of them is 0, the output will be 0. So only this will produce a 1, all the 3 combinations will give a 0. So now this is our result from the right side, this is our result from the left side. If both of them are equivalent, then means that we have proved it, and in our case we can see that both of them are equivalent. So by this way we have proved the De Morgan's law. When we talk about precedence of the operator, parenthesis comes first, then the complements, then and then OR operator. Parenthesis not and OR. Now Boolean functions. Boolean function is an algebra that deals with binary variables and logic operators. We have binary variables. Binary operators are OR and. Unary operator is not. What we say, binary variables are 0. We can have binary variables x, y, z. We can name name it, and all these x and y variables can have only 2 values, that is 0 and 1. Binary operator means those operators which have 2 inputs. Can be x, y, can be a, b, can name c, d, whatever you like, and or and will produce one output, that is binary variable. Will be binary variable. Unary operator means that only one input goes to this operator and produces an output. Parenthesis we all know, when we have want to emphasize on any operation or have to give have to separate it, we use parenthesis. By Boolean functions, usually we write in this way. This left hand side is our function or the output, and we usually give it f with a subscript to just define the number. And you can have different names also. And on the right side, usually have equation as in our arithmetical algebra. In Boolean functions, we have, for example, x, y, z bar. It means that we have applied AND gate on x, y, and z bar. And z bar means that we have to complement of z. So in this way, we have different Boolean functions for different things. Now, when we have Boolean functions, as I said before, we have 3 things. First, we define our Boolean function with the help of an expression, Boolean expression like here. We have this; these are Boolean expressions. We can express our Boolean function in form of a Boolean expression, or we can have we can also represent or we can say all the possible combinations with the help of a truth table. Truth table of 2 raised to power n entries. For example, if we have 3 inputs x, y, and z. So for 2 raised to power 3 is our 8 combination. We'll have 8 combination. These combination will start first with we'll consider that all these 3 are zeros. Then we'll say that z was 1. Then we'll say y was 1. Then y and z was 1. Then 1 0 and so on. All these combination till all of 3 inputs are 1. Then we can calculate our outputs f1, f2, f3 and f4, and we have separate columns for all these. f1, x, y, z bar we can perform and so on. There can be that we have 2 different Boolean expressions, but they have the same function. For example, if we see f1, f2, f3 and 4, f3 and f4 are exactly the same. That is this and this, and f3 have more values, or I should say the expression is longer, whereas f4 is the shorter. It means that both of these are representing same function, but f4 is the shorter version of f3 or reduced version of f4. And in later of our subject or chapters, we'll discuss how can we reduce our functions or our Boolean expressions. Then first, as I said, we can express our Boolean function with the help of Boolean equations. Secondly, we have truth table, and third is that we have our logic gates, or we implement our Boolean function with help of logic gates, where this is for NOT, this is AND gate, and this is for OR. So let us first see F1, or F2, x plus y bar z, x plus y bar z. So first we'll perform y not, we have a y bar here now, then we have a z, both of them is and we get y bar z here. Then this goes to OR gate, also x is also input to the OR gate, and F2 will be x plus y bar z. In this same manner, F3 and F4 is implemented. If I talk about F1, F1 will be x, y, and z. This is NOT gate. On all 3 of them, go to AND gate and get F1. Now, in the last slide, we said that F3 and F4 are same. Their function is same, but the expressions were different. And if you see the implementation here, we have 2 NOT gates. We have 2 NOT gates in F4 also. 3 AND, we have 2 AND, and we have 1 OR gate, and we have 1 OR gate. F3 and 4, basically both of them are representing the same things, but F3 is using more gates. How we have 3 AND and 2 AND, and also these AND gates are 3 input AND gates, where these are 2. Similarly, OR gate, here are 3 out input OR, and here 2. So if we talk about F3 and 4, F4 is more economical in the sense that it is less will cost less because number of gates are reduced. So we can can have more expression, more than one expressions for a function, and it also happens that one of them, the expression would be more economical than other. Of a Boolean expression, some few things which we should know. Literal is a primed or unprimed variable. Primed or unprimed means it can be a complement or can be a non-complement variable, and input to a gate. It's a literal. For example, if we talk about x bar, so x is a literal here. Term and implementation with a gate. Term is an implementation with the gate. For example, x dot y, here x and y are two literals, and x and y, this is a term. X bar is a term, x y is a term. So in terms we have literals. Literals can be primed, unprimed, we can take a complement, or we can have a non-complemented. The minimization of a number of literals, number of terms, means that when we talk about minimizing of a Boolean expression, it means that we will minimize number of literals and number of terms. When we reduce these number of literals and terms, we basically will reduce the equipment, will reduce the hardware of a circuit will be smaller. This is a hard problem. There is no specific rule to follow. And for example, if we have x bar plus y, first we'll use some postulates and theorems to open it or to solve it. We have x bar plus xy. Now we know x bar is 0, and 0 plus xy is 0. So now we have reduced x bar plus y to x and y. Similarly, this will happen. Here we have x plus y complement. We have an AND gate in between. First we use the distributive law, x plus y plus xy bar plus y bar, and then we know that this will be a 0, y bar, and then we will be left with x plus xy plus xy bar, x taking common, 1 plus y bar, y plus y bar is 0, and 0 plus 1 is, sorry, y plus y bar is 1, and 1 plus 1 is 1, so x dot 1 is x. So basically you are using the previous postulates and theorem where we think can be applied, and we solve it. In this process, we can be wrong and we can be right, or we can miss it, or it also happens that we can further minimize the expression, but using postulates and theorem we didn't reach the minimum numbers of literals and numbers terms. xy plus x bar z plus yz. So now these terms, there are three terms with two literals. First, what we have done, xy plus x bar z. Here y with y of z, x and x bar, it's two literals, we'll make it three literals. How we can make? Basically we'll use an AND gate with x plus x bar. Now x plus x bar basically is a 1, and when anything is AND with the 1, it is gives this yz back. So basically this yz is equivalent to this. So after we have xy, x bar z, xyz plus x bar yz. Now we'll use xy, this xy, and this, both these terms will take xy common, we'll have 1 plus z, and here x bar z and x bar z will take common, and we'll have 1 plus y. So we have xy, because 1 plus z is 1, 1 plus y is 1, so we'll be left with xy plus x bar z. So this is a minimum. Here we have three terms. Here we have two terms with two literals. Number 6 is the dual of number 5, so we can use the duality from the previous and we can have the answer, which means that we don't have to solve it, we have this answer, and instead of or we'll use and, in the place of or we'll use and in the place of and we'll use or. X and y will become x plus y, x bar and z will become x bar plus z, and in between of them was plus, which will be replaced with and. Now comes complement of a function. Before we talk about complement of a variable, that is x bar, y bar. Now when we talk about a complement of a function, the of f is f bar and is obtained from two things. First of all, we'll interchange zeros with 1 and ones with 0 in the value of f. And secondly, by De Morgan's theorems, we'll have a plus b plus c. If we have a plus b plus c and we take a complement of it, this is equivalent to, let us assume that b plus c is x, just to understand what happens. So now we say a plus x is the complement, a plus x complement of a plus x. So from the De Morgan's law, we know that a plus x whole complement is basically equal to a complement and x complement. This we have on the table of the postulates and theorem. A bar, x bar. Now a bar, and we all know x was basically b plus c. We'll have b plus c whole bar. Now again we'll apply De Morgan's on b plus c whole bar, and it gives b bar, c bar. So we have a bar, b bar, c bar. So this is applying associative law. A plus b plus c whole bar is equivalent to a bar, b bar, c. C, because c was c bar. C bar. So generalized form of the De Morgan's law is that wherever we have a plus, it will be replaced with an, and wherever we have an and, we replace with on. The difference between De Morgan's and duality is that in duality we don't change the complement of the literals, but in De Morgan's, or when we talk about complement, the prime number will become unprime and the unprime will become prime. So, as I said before, complement of a function is obtained by interchanging and or operators and complementing each literals. For example, we have here a complement of a function x bar y z bar plus x bar y bar z, and another. So first we'll talk about f1, x bar y z bar and x bar y bar z. X bar y bar z is equivalent, first of all, x y z bar plus x bar y bar and z. First we change the gates, the first step. So this or will be and. So we have x bar y z bar. We change the gates in steps, and x bar y z y bar z. Then we'll change the operator between these literals, or in the term we'll have x bar plus y plus z bar, x bar plus y bar plus z. And lastly, we'll take complement of all the literals. Then we'll have x was bar, we'll have x, y will become y bar, z bar will become z, then x bar will become x plus y plus z bar. So this is what we have the answer. In similar way, we can solve f2, and that is x y bar z bar plus y of z. So De Morgan's means that x bar plus y bar z bar plus y z ka whole bar. So now we'll use the De Morgan's law here. Y bar z bar will become y bar z bar plus y z whole complement will become y bar z bar complement dot y z complement. Now again applying De Morgan's, y bar z bar is y plus z, and y z whole bar is y bar plus z bar. So a simpler procedure is that we take the dual of the function and then we complement each literals. Like if we have the same f1 x bar y bar z bar plus x bar y bar z, as I said before, we'll take the dual. Dual means that replace or interchange and or. Here if we have and will replace with or, and will be replaced with or. There is a or will replace with and gate, and then in between these literals its and gate will replace with or. After duality, the next step will complement each literal. So x bar will become x, y will become y bar, z bar will become z, and so on. In this way we can have the complement of a function. This becomes here is the end of this lecture. Thank you.